Welcome back, guys. In this fourth lecture, we are going to discuss what do we mean by weak derivative and when a function is weakly differentiable, or how can we define weak differentiability of a function. So first of all, I'll define and then we'll discuss a couple of examples that, okay, for what functions we can define their weak derivative and for what functions we can't. And I think this lecture won't be too long. So maybe 20 to 30 minutes, depends. So let us begin with, let us take a subset of Rn and our f is in from L1 of omega. And we have already discussed what do we mean by a function in L1 space. So let me just remind you, it means that I raise f to power 1 and I integrate this over this omega, and this whole integral should be finite for f. Then I say that, okay, this function is in L1, otherwise this function is not in L1. And omega is the whole set. It can be whole Rn, let's say R1, or R2, or whole R3. And yeah, if omega is finite, then we can discuss maybe these things in a different way. Okay, f is in L1. We say f is weakly differentiable. We say that the weak derivative of f exists if there exists a sequence, let's say g1 up to gn, of the functions which are also in L1. So these functions should be in L1 such that if I take any phi, which is C infinity function with the compact support, you know very well these functions are infinitely differentiable and all the derivatives are continuous and they have a compact support. It means on some compact set, they are non-zero, and beyond that set, these functions are zero. And we discussed one example in previous lecture as well that was about modifiers. Okay. So what happens that if I take f and I multiply it with the derivative of f with respect to xi, and I integrate it over whole omega, it should be same as negative of the ith function, the integral of gi times phi dx. So like then we say that, okay, this f is weakly differentiable. But the question is, what is the weak derivative of f? So the weak derivative of f with respect to xi is going to be gi. It means when I say what is the derivative of f with respect to x1, you will say g1. What is the derivative of f with respect to x2, you will say g2. So if this equality is satisfied, it means we say that the weak derivative of f exists. We'll come to examples and then we'll come to know that, okay, why that is so. There's some sort of notation, okay. If I differentiate f with respect to ith component, that is di of f is equal to gi. We say this is the weak derivative of f. Weak derivative of f. And the second thing is the whole derivative of f is defined to be a vector d1f, which has components d1f, d2f up to dnf, and which is simply the first derivative. The derivative of f in the first component is g1, and the second component is g2 up to nth component is gn. So this is like how you define the weak derivative and once this equality is satisfied in terms of integrals, you say that the function is weakly differentiable. Let us come to an example. I am taking a very famous example of the modulus function or absolute value function. And this function is L1 from -1 to 1. And what is the shape of this function? It simply looks like this. So the function is like, it has slope +1 here and slope -1 here. You know very well it's a derivative, but the problem is we cannot define the derivative of this function at 0. So it's the classical derivative, but we can define the weak derivative of this function. And we'll say that, okay, what is the weak derivative of this function? Since this function has only one component x, there is no x1, x2, or there is no xy. So we are going to just differentiate this with respect to x. But we cannot differentiate at 0. But we can make sense of the derivative at 0 in a weak sense. So let us discuss, or let us see what can we do. So I will take this left hand side from here, you know very well, this is the left hand side. So what am I doing? I'm writing f times phi prime. Phi prime is the derivative of phi, you know very well, dx, and I'm going to integrate it over the set omega, but my set omega is from -1 to 1. So now I will come to know that, okay, what is my g? Just I have to simplify this. I have to play a little bit with these, all the things. Okay. So -1 to 1, my f is absolute value of x times phi prime dx. But you know very well, how can I define mod of x? So it's from -1 to 0, and from 0 to 1, it has two different values. You know very well how you define mod of x. So it's negative x here, and it's positive x here, times phi prime dx times phi prime dx. Now I'm going to integrate this thing by parts, and you know very well how to integrate by parts, and I'm doing the same thing. So I'm writing here integration by parts. So just you know very well, you have to keep one function same and you have to integrate other function and so on and so forth. So I'm going to keep negative x same, and integrating phi prime will give me phi, and I'm going to evaluate this from -1 to 0 minus integral negative x m, sorry, derivative of u, that's going to be -1 times phi dx. So this is integration by parts for the first integral. And for the second integral, again, x m phi evaluated from 0 to 1, and what else? Minus derivative of x is 1, and 1 times phi dx. So what can I do further? I will evaluate this function at 0 and then at -1. So if I evaluate at 0, this becomes 0, because if I put x is equal to 0, this becomes 0. And at -1, this is also 0. So why this is 0? Because I have already taken this phi to be C infinity with compact support over the set omega. This is how we define phi. But the question is, what is omega? In our case, omega is -1 to 1. It means this phi should be equal to 0 at -1 and 1. This is the main thing. This is the main thing that we are using. So this whole term goes to 0. Similarly, this whole term goes to 0, because if you evaluate this phi at 1, this is 0. And if you evaluate at 0, this is going to be 0. So these two terms vanish. And what is left with us, that you can see easily, minus -1, sorry, this should be 0, -1 to 0, minus 1 times phi dx, minus 0 to 1, 1 phi dx. So I can write this thing in a clear way that, okay, this is -1 to 1 g times phi dx. So this is my right hand side, g times phi dx with a negative sign in front, which you can see here. Gi is ith component, but I have only one g, I have only one x, so it would be only one g. So what is my g? You can see that, okay, the value of g from -1 to 0 is -1, and from 0 to 1 it's 1. This is how I define g. This is the weak derivative of this function. So what is the weak derivative? How can I define g? So if x is from what do we say, -1 to 0, x is equal to 0, and x is greater than 0 and less than or equal to 1. From -1 to 0, it's -1, and from 0 to 1, it's 1. And for x is equal to 0, we can put any constant, doesn't matter, because we don't know what is the value. So it's any constant, let's say c. So this is the weak derivative of the function f that I have defined so far already. So if I have this function mod of x, which looks like this, you know very well, its slope here is -1, here is +1. That's a classical derivative. But the problem is, what is the derivative at 0? So you cannot say the derivative at 0 is c. But in the weak sense, you can say that, okay, the derivative of f is this function g, and g is defined in this way. From -1 to 0, it's -1, and so on. So this is how you define the weak derivative and how you find out the weak derivative of a function at a point. Okay, so like you cannot say that, okay, on this point, the weak derivative of this function is this. The weak derivative is also always written or made sense in terms of integrals. You cannot think outside integrals when we are talking about weak derivatives. So I'm taking another example, and maybe for this example, we'll see that, okay, the weak derivative does not exist. One thing is that whatever g you get, it must, this g must belong to L1 as well, from -1 to 1. So this must be in L1 from -1 to 1. Like if you integrate this function from -1 to 1, you should get something, a finite number. It should not be like infinity. So the second example is, I'm taking the function which is signum, some people call it sine function or signum function, on -1 to 1. So what is our motive? Our motive to find g such that for all phi which are C infinity compact support from -1 to 1, such that what happens, -1 to 1 f times phi prime dx should be same as -1 to 1 g times phi dx. So this is f and this is g. So we say that the weak derivative of f is g if this equality is satisfied. Now we have to find out what is that g. If we are able to find out the g, then we are done. But we have to just keep one thing in mind, g must be in L1 of whatever the domain you have. So this L1 condition is really important. So, and I gave you an example that, okay, what function is L1 and what function is not L1. We can discuss some examples maybe. I'm taking a function f of x. Let's say I'm naming it f1 of x. And I'm talking about, let's say, I'm talking about whole domain, e to the negative x square. So this function, I think looks like this. It's a bell type curve and it looks like this. So the question is, when I integrate this from -1 to 1, e to the negative x square dx, what's my answer? Not -1 to 1, from negative infinity to positive infinity. I think this is the square root of pi. And you can find this thing easily, and which is finite, because this is this area under the curve and this is finite, so you're done. e to the negative x squared dx. Yeah. Similarly, so I say that, okay, this function belongs to L1 over whole R. The second example that I'm going to give you, let's say f2 of x, let me just use a different color. f2 of x, which is, let's say I'm using, what function I'm taking? 1 over x? No, okay. So I'm taking e to the x, or e to the negative x. And this function can be, let's say L1 over some, let's say, finite set or some compact set, but this cannot be L1 over whole R. This does not belong to L1 over whole R, and you can check this thing. Okay, I raised to this 1. You have to raise this to 1, but absolute value is necessary because it makes positive, but exponential functions are always positive. Then the power 1 doesn't matter. So negative infinity to infinity dx. And what you simply do, the integral of ex is ex, and just you apply limits from negative infinity to infinity. So this simply becomes infinity because e to the infinity is infinity and e to the negative infinity approaches to 0. But one term is infinity. So, and how does the function look like? So it's e to the x, so the function looks like this. So you know very well, you cannot find this whole area because this area goes on over here. So you cannot find out this whole area under the curve. Hence, this is like a simple explanation. Otherwise, you can make sense of what functions are in L1 and what functions are not in L1. Okay, but you can say one thing, that okay, this F2 belongs to L1 if you restrict yourself to a smaller set. Let's say you take a set from negative infinity to 0. Then this is L1. So you have to change the functions and you have to change the domains of the functions where they're defined. Then you can say, okay, this is in L1 and this is not in L1. This can be done. So next thing that I'm going to discuss, so I have to do the previous example that I mentioned so far about the weak derivative of a function. But before that, I'm going to define what do I mean by a function we call a delta function. So, and this delta function is really important. It's not a function, it's a functional. Delta functional. And how do you define this functional? So one thing is that this delta of x is not a function, but we can define this in terms of a function. This takes value 0 or infinity. So when x is not equal to 0, this is 0. And when x is equal to 0, or this argument is equal to 0, this function takes value infinity, or it's not defined over there. So I'm just giving this a quotation mark because we cannot say what an infinity is. And the graph of this function looks like this. So it's 0 everywhere. So at x is equal to 0, it has some sort of kink like this. And for both of these sides, this is 0. And this is, let's say, infinity here. So it's like 0, but at 0, it has some sort of kink like this. So it's like this at 0. And for rest of the times, it is 0. Okay. Why I'm going to define this function, this is really crucial because I'm applying in this example, and then we'll be applying this function most of the times. And one thing else, if you integrate this function over whole R from negative infinity to infinity, the result should be 1. This is one other result, one other remark. But this is really not important thing because in the classical theory of analysis, it doesn't make any sense. What makes sense, we'll discuss, because we'll say that, okay, delta is a functional, it's not a function. So when we discuss these things in detail, we'll discuss this thing as well. Okay, so, and one thing else, that if you operate delta x to some function x, and this is the inner product, or what do you mean by this? From negative infinity to infinity, you multiply delta by some function x, and you simply integrate this. This is going to be the value of f evaluated at 0. This is the second most important thing that you have to keep in your mind. So this thing, delta operated on some f, because delta is a functional, so you can operate on some function. So it is simply the function evaluated at 0. And maybe the third remark that I want to put, I don't want to discuss these things in detail, because these are not too much technical. These are the things that you can do, or you can see from any engineering mathematics book. But the thing that is important is delta is not in L1. So you can simply make sense that, okay, if I raise this thing to 1 and I integrate, this is 1, which is finite, why this is not in L1? So this is the difference between, like, L1 is a space of functions, but I'm saying that delta is not a function. So how can I say it's going to satisfy some sort of integral properties? So this is the problem. So engineers do make sense like this, the first thing that we have discussed so far. But for mathematician, for analysts, this doesn't make sense. So this is my claim, and I'm going to prove this claim. So this is my claim. And what is the proof of this claim? And I'll be using this proof. I'll be using this result when I'm going to find out the derivative of the function. Okay. So what is my claim? My claim is, okay, suppose delta is in L1. This is my supposition, and this will lead me to some sort of contradiction. So I'm taking a sequence of functions that are C infinity or compact set from -1 to 1. So I'm taking this sequence, and I'm defining these all phi j's at 0 to be 1. And I'm saying that the phi j takes value between 0 and 1. This is my claim. It means how these functions look like. So they are always between -1 and 1. At 1, they all take value. Sorry, at 0, they all take value 1. And their graph look like this. So if you take one function, it looks like this. If you take another function, it looks like this. If you take third function, it looks like this. So these are like the sequence of functions that I've defined so far. Now, their value is between 0 and 1. And at 0, they have exactly value 1. And they have non-zero values between -1 and 1. Beyond that, that's going to be 0. This is what we say. They have compact support. Okay. Now I'm taking another sequence of functions, fj, which is delta functional times these phi j's. And when you take the absolute value of these fj's, this should always be less than delta x. Because when you take the absolute value of fj, this is absolute value of delta x and absolute value of phi j of x. But you know very well, this thing is always less than or equal to 1, and this thing is positive. So this is less than or equal to delta of x. So if j's are less than or equal to some function which is integrable, and why delta is integrable? Because we have claimed so far over here that delta is in L1. It means this delta is integrable. This is our claim, but this claim will lead us to some sort of contradiction. And one thing else, these fj's go to 0 almost everywhere. Why? Because delta function is 0 almost everywhere. At one point, it has value infinity, but that one point in the measure theoretic sense, it has measure 0. So we do not like think of that one point. So delta function is 0 everywhere except one point. It means we say the delta function is 0 almost everywhere. Now I'll use Lebesgue dominated convergence theorem. One thing is that if I take delta and multiply it with phi j and I integrate, what is this going to be? You know very well, this is the function fj. This is how I define it, fj. And these fj's are 0 almost everywhere. So if I take their limit as j go to infinity, these become 0 and the integral of 0 is 0. But on the other hand, you know very well that how do you define this delta function? This delta function is defined as when you have this integral, this means that you have to evaluate this function phi j at 0, but phi j at 0 is equal to 1. So you got that, okay, 1 is equal to 0. So you got that 1 is equal to 0, which is a contradiction. So on one side you are getting 1 and on another side you are getting 0. This is simply a contradiction. And why this contradiction occurs? Because we have assumed delta function to be integrable. If we are assuming delta function is not integrable, then simply we cannot apply limits here, because we can apply limits because of Lebesgue dominated convergence theorem. And Lebesgue dominated convergence theorem, why we can apply? Because delta function is, we have assumed it is L1. So here we have applied what we say. I think in this limit we have applied LDCT, Lebesgue dominated convergence theorem, and that we have already discussed in our I think second lecture about measure theory. Okay, I'm not going ahead, and I'm just going to discuss what is going to be the derivative of this function f that we have defined so far, the sine function on this, and we have to satisfy this relationship for a g which is in L1. So I'm going to simply solution of example 2. So let me call this example 2. So this is the solution of example 2. So what am I doing? So I'm taking -1 to 1 and I'm taking sine function and I'm multiplying phi of x dx. I'll just integrate and I'll come to know that, okay, what is my g? So you know very well, from -1 to 0 and from 0 to 1, we have two different functions because this is a sine function. So from -1 to 0, it's -1. And from 0 to 1, it's 1. And I'll multiply here what? Phi, sorry, this should be phi prime of x according to the definition. Dx, sorry, plus phi prime of x dx. So I'm taking this negative outside and the integral of phi prime is phi. Now I'm evaluating phi at 0 minus phi at -1. Plus, again, I'm integrating phi prime, that would be phi, and I'm evaluating at 1 and 0. Phi of 1 minus phi of 0. So you know very well, phi at -1 is 0 because it is compact support. Sorry. Phi at 1 is also 0. So I'm left with negative phi of 0 and negative phi of 0, which becomes -2 times phi of 0. So how can I write this thing? Let me tell you, I can write this thing as negative because in the weak derivative, I want negative, and -1 to 1, this is my limit, phi of x dx, but what should I multiply here to get this thing? 2 times phi of 0. So the simple answer is 2 times delta of x, because when I operate delta of x on phi of x, it is simply phi evaluated at 0. So you can simply say that this satisfies the definition of weak derivative. You have You have negative 1 to 1 limit on both sides. On this side, you have a negative sign. You have phi prime on left hand side and phi on right hand side. The function whose derivative you are going to find is sine, and the derivative is 2 delta of x. But we have already discussed the derivative is g. G must be in L1. Unfortunately, this 2 times delta x is not in L1 from negative 1 to 1. This is not in L1. So the story is closed. Hence, there does not exist some sort of weak derivative of the sine function, because this is not L1. This is not in L1. So the derivative is, this is a wrong statement, but I'm saying the derivative is 2 times delta x. But since this is not in L1, so we cannot say that there exists a weak derivative of this function. But the derivative of this function exists in the distribution sense. When we'll discuss distributions, we'll discuss distributional derivatives, then we'll discuss these all the things. So wait for the next lecture, and next a few lectures we'll be just clearing these all the things. So I think today's lecture was not that much hard, and if you just understand the definition and the examples, you will make sense of these all the things. So see you in the next lecture. Till then, goodbye.